Hi and welcome. I'm trying to learn cytology, today osmosis, and after we've done it, we're going to do extensor carpi ionosis strength training. And if you participate in the extensor carpi ionosis strength training, then it's a video on this. And this is part 3 or something of which we are reading about osmosis. The tonicity of a solution affects the volume and shape of body cells by causing osmosis of water into or out of them. So whatever the tonicity is, it affects the shape of a body cell by allowing water in or out of it. Normally the osmotic pressure of a cytosol is the same as the osmotic pressure of the interstitial fluid outside cells. So the osmotic pressure was a solution containing solute particles that cannot cross the membrane exert a force called the osmotic pressure. We don't really understand it, so this is part 3 of half a page. So it is about the water. So there is water, 100% water on one side and 70% water and 30% solution on the other side. The solution can't go through the membrane in the center. The higher concentration of water, 100%, wants to go to the other side where 70% are, so that it becomes on both sides the same amount of water. Now there is already more in the other side because there's 30% solute, but the solute can't go over, so water is still going over as long as there's not enough pressure. I think of gravity, they called it something hypertonic solution, hypertonic pressure or something, which is pushing it back. And now one of them is the osmotic pressure. I think the osmotic pressure was the amount of pressure the solute has now because the solute can't go over. I don't really get it. And the tonicity is something I don't know where it was not explained. Normally the osmotic pressure of a cytosol is the same as the osmotic pressure of the interstitial fluid outside cells. So whatever there is for pressure, the pressure from the inside of the cells is the same as on the outside. There's the same amount of pressure on something of it to go out as there is of something to go in. Because the osmotic pressure on both sides of the plasma membrane, which is selectively permeable, is the same, cell volume remains relatively constant. Any solution in which a cell, for example a red blood cell, RBC, red blood cell, maintains its normal shape and volume is called an isotonic solution. So they mean the cell itself is an isotonic solution. This is a solution in which the concentration of solutes that cannot cross the plasma membrane are the same on both sides of the membrane. So the osmotic pressure, I think, is it, but what doesn't know the tonicity? The tonicity. So there's the same amount of things which can't over, so now on both sides are 30% of something which can't go over as on the other sides. And there's the same amount of, it was about the amount of pressure which would be necessary to press it down to bring on both sides again even levels. There's not even level because the higher amount of water concentration wants to go over and puts more water in, even though there is still something filled, there is already something filled with solute. And the amount of pressure necessary to put it in, to bring it again onto the same side, is the pressure, the osmotic pressure. And there is now the same amount of osmotic pressure in most cells on the inside as on the outside. And that makes them to be isotonic solutions. Under ordinary circumstances, a 0.9% sodium chloride or table salt solution called a normal saline solution is isotonic for red blood cells. Okay, I don't really know what we mean there, but a normal solution of water with a little salt in it, like a little salt water, is isotonic to red blood cells because I think the 0.9% of salt has so much of osmotic pressure as there is osmotic pressure inside of a cell. Maybe because there as well in a red blood cell 0.9% of stuff which can't go through the membrane of a cell. And from the outside water could go in, but not the 0.9% of water, the salt can go into the red blood cells. I think that is what I'm talking about. Whereas the red blood cell plasma membrane permits the water to move back and forth, it behaves as though it is impermeable for natrium chloride, for sodium plus and chloride minus the solutes. Any sodium plus and chloride minus ions that enter the cell through channels or transporters are immediately moved back out by active transport or other means. These ions thus behave as though they cannot penetrate the membrane. Are actually the same one transported out, or just the same one, or possibly another one? I don't get it. Why do they go not in? But they're transported out again. So the net, we call it net, something with net. The net diffusion is 0. Because the same going in as out. But why is something going in? I thought salt carbon can go in, but why is the salt transported out again? When red blood cells are bathed in 0.9% sodium chloride, water molecules enter and exit at the same rate, allowing the red blood cells to keep a normal shape and volume. Yes, water goes in and out in the same amount. But why with sodium chloride? The same amount comes in as out, and therefore it doesn't change its shape, it isn't bulging up. A different situation results if the red blood cells are placed in a solution that has a lower concentration of solutes than the cytosol inside the red blood cells. This is called a hypotonic solution. So the solution itself, not the red blood cell. In this state, water molecules enter the cells faster than they leave, causing the red blood cells to swell and eventually to burst. Why do they burst? Is the osmotic pressure greater as the red blood cells can withstand? The rupture of red blood cells in this manner is called hemolysis. Pure water is strongly hypotonic. Pure water is strongly hypotonic. That sounds dangerous. I mean, we're talking about red blood cells which are getting destroyed by pure water. Now, this is not medical advice or something, just fantasizing around before the curtain here. Okay, we're saying pure water does not have salt in it, and therefore there's more water going in as water can go out, because inside of the red blood cells there's not just water, that could then just change, but there is also some type of solute and some other stuff which will not pass out, and therefore more water will go in as can go out, and it seems to continue as long until the red blood cell bursts. A hypertonic is just an example, just hypothetically would it burst, or would it do it actually? A hypertonic solution has a higher concentration of solutes. A hypertonic solution has a higher concentration of solutes than does the cytosol inside red blood cells. Now we're having hyper, so stronger. Hyper, the other one was hypo. So hypo, there was no solute in it, it was pure water. Now we're having hypertonic. Now a lot of things which make tonicity, whatever it was. It wasn't really explained. We're going to read that later again. Now knowing what hypertonic and hypotonic are solutions. And the solutions seem to be that, not the cell itself. But why should not the inside of such a cell also be hypertonic or hypotonic? There could be a cell with pure water in it. It would be a hypotonic cell. What makes something hypotonic? It can't be the 0.9% benchmark. It has to be in comparison to something else. A hypertonic solution has a higher concentration of solutes than does the cytosol inside red blood cells. One example of a hypertonic solution is a 2% natrium chloride solution. So now we're having again salt water, but it is more salty. In such a solution, water molecules, is that a reason why things dry out if they are salt, they are not drying out? But there is happening something with salt water, if cells are in it, or if organic material is in there. One example of a hypertonic solution is a 2% natrium chloride solution. In such a solution, just from the chemical aspects, what are the differences between bathing in drinking water with around 0% of salt, or in ocean water with the Atlantic has 35% or something? Just the chemical differences. In such a solution, water molecules move out of the cells faster than they enter, causing the cell to shrink. The shrinkage of red blood cells in this manner is called oxygenation. Red blood cells and our body cells may be damaged or destroyed if exposed to hypertonic or hypotonic solutions. Hypertonic or hypotonic can both destroy it by causing it to shrink, by hypertonic if more is going out than in, or hypotonic and more is going in when we're bursting. For this reason, most intravenous solutions which are infused into the blood of patients are isotonic. That means it has the solution has the same as the red blood cells. So people who are giving intravenous injection into the arm are looked with the thing which is brought in has the same amount of solute substances or whatever in it as red blood cells have. Okay, and that was the osmosis part. If you were here for cytology, you can go directly to the next part of cytology, and we will continue reading a bit on, and then at one time we come back to osmosis, to that article, read it again, knowing a bit more what we're explaining there, and then we're trying to make it in a presentation and saying there what we read there. If you stay here, if you were here for that, you can go to the next part. If you stay here and participate in the extensor carpal ulnaris strength training, then it's at your desk. Go to still stand, arms up, hands on the fists, and bring them down. And up. And our hands like that, and again down. And up. We have here 3 rules. The first rule is that we're stopping immediately as soon as there's pain. The second rule is that we go only as far as we can go with a little bit of effort. And the third rule is that we're not overdoing it. We just want to strengthen, not to exhaust. You can use now a t-shirt, a towel, or sock, press onto it, and bring the hand down. And up. Again down. And up. And the other hand. Press and down. And the other hand, press and to the outside. And press evenly with all 5 fingers. Other hand, press and out. And again the other hand, press and from top, press and down. And up. Down. And again. And the other hand, press it down. And up. And just press in neutral position and the other hand. And that was the extensor carpal ulnaris strength training. I thank you very much.